Hi everybody, welcome to the SETI Institute in Mountain View, California. Thank you for joining us for another Facebook Live segment. My name is Matt Tiscareno. I'm one of the scientists here at the Institute, and today we are here to interview Mark Showalter, also one of our scientists, for a very exciting new discovery. So Mark, why don't you tell us what the discovery is?
Yes, well, we have just had a paper come out in the Nature magazine today, and it's about the discovery of the 14th moon of Pluto. It's a very little moon. You can actually see it. This is one of the discoveries. Hubble image, and we did all of this work using Hubble, but to see the little moons of Neptune, you have to just basically way overexpose Neptune itself. So I've just drawn in the shape of Neptune because otherwise you can't really see it in our images. But when you clean up the images and do a great deal of work, what we found is a little dot out of Greek mythology, having to do with the creature with the head of a horse and the tail of a fish.
Indeed. And then we have it there as an inset is the gory detail of exactly what you saw Hippocamp to look like. So it's quite photogenic.
Well, photogenic to me and photogenic to you, Matt, probably isn't photogenic to everybody. You know, what you're seeing here is mostly noise, of course. A lot of people don't quite realize how genuinely ugly the images are that we take from the Hubble telescope. But when you want to do something like this kind of work, you have to really push the instrument to its extremes, and that means there are a lot of flaws and artifacts that you have to deal with. But nevertheless, we are able to find an object that was missed by the Voyager cameras when it had the opportunity up so close.
Indeed. How long have you been working on this project?
It's very gratifying to say. This is now essentially 15 years of work. I won't say it's 15 continuous years of work. I've had a few other things to do in the meantime. But we got our earliest data in 2004. That was the first time we got some time on the Hubble telescope to look at the Neptune system. We had a couple of reasons for doing that. We wanted to see what these arcs look like. These arcs were seen by Voyager. The Voyager flyby was in 1989, but we realized that the camera on Hubble was powerful. We had the data from 2004, but it wasn't until 2013 when I was essentially wrapping up this whole analysis and said, you know, there's one more thing I could try with that data that I hadn't really pushed on it quite hard enough. We had this special technique that sort of stops the moons in their tracks, which is a way of taking a bunch of separate images and combining them into one longer exposure image. And I had done that for parts of the image, but I hadn't done it for the whole image. So I decided, okay, I'm writing the final report, but I better give this one last thing a try. And of course, that's when we turned out that we did that processing, an extra dot turned up. And then we had to go back and do a whole lot more work to get to the point we are now ready to talk about today.
Right. So to do this technique, if I remember correctly, you need to assume that it has a fairly regular orbit, right? You couldn't necessarily find something on a completely crazy orbit, you know, high inclination, orbiting backwards or something. So you start with that assumption, and then you kind of account for that. Go ahead and tell us more about that.
Yeah. So the idea here was that even Thalassa, which we knew about already, was a moon that did not show up in one image, but we had 8 5-minute exposures. This is about a 5-minute exposure. And so what we had to do is figure out a way to say, okay, for at least 7 of these, I'm going to leave one image alone out of our 8. And now all the others I'm going to say, if there's a dot here, if there's a moon here, where would it have been at the time of that other image? And so we essentially shifted.
Assuming that it has a well-behaved
Assuming it's doing the kind of orbital motion that all these little moons are doing. And so we essentially did these twist processing of moving everything back, saying, if it's here now, where would it have been then? And when we did that, we finally had 8 images that were effectively as if they had been taken at the same time. And then we could stack them up. And then I was delighted to see Thalassa, and I was delighted to see much brighter detections of these other little moons. But that little dot down there in the red box wasn't on the original image, I should add, but the red box caught my eye.
So now, our sharpest listeners may be aware that the existence of this moon was announced some years ago.
Yes.
What exactly is new today?
Yes. So that the way that things work in the astronomical community. Are there technical issues here?
Yes, we're having some technical issues.
Excuse us for
Apparently,
our technical issues.
Sound is cutting out when we just focus on the monitor, so I'm just seeing.
So
if
don't
we can
focus
fix
on the
that.
monitor.
Yeah.
Okay, are we good to
Sorry,
continue?
sorry. Yeah. Oh, yeah. You guys are good to continue.
Okay.
Okay,
Also,
what's
you
new?
should say hi to Robert French while you're out there.
Hi, Rob.
Hey, Rob. My co-author Robert French couldn't be here today, but he was very much involved in a lot of this data analysis. So when we made the discovery, that's when you make an announcement. It's always important in astronomy to get these new results out as quickly as possible. So in 2013, we'd seen that little dot, and we'd seen the same dot a couple of more times over. So we put out what's called an IAU circular for the international astronomical community to see it. And there was a little bit of press coverage at that time coming out of the Space Telescope Science Institute. But that was just the beginning, really, of the work involved. Then we had to go back and reprocess every image. We also got some more time on the telescope, which was very useful for us because it enabled us to pin down the orbit much better. We were able to figure out the orbit well enough that we could go back and check the Voyager images, because really, why did this thing not show up in Voyager? Turns out Voyager missed. There's actually one really fantastic image of Proteus from the Voyager flyby, and when we calculate where Hippocamp was at that time, it was like outside the image by about 100 pixels. So it was just a bare miss, but
Wow.
It was a miss. And so all of that information we got to put together, we determined the size, and in fact, I think the most interesting part that comes out of our work is that now we realize Hippocamp is in a very strange place in the system. It's very close to a much larger moon called Proteus,
Yes.
and that's the story of how Hippocamp came to be is kind of the big surprise, I think, that comes out of our paper.
Right, we will get to that. So what's
Sure.
new today is that you've done the work that we will just talk about as to why Hippocamp has an interesting orbit,
Yes.
and the science that we have learned about it. But the other thing that's new today is the name.
Yes.
So why don't you tell us what? So this moon used to be called Neptune XIV or Neptune 14 or some combination of years and letters.
S/2004 Space N Space 1.
There you go. Because it was the first moon of Neptune discovered in 2004.
Well,
but you
no,
didn't discover it in 2004.
no, not even that. It was the first moon of Neptune discovered in data obtained in 2004, even though the year at the time that we made the discovery was 2013.
That's right.
So it's the year of the data, not the year of the
So we
discovery.
now have a much more mellifluous name.
So even N14 was part of the approval process that we had to go through with the IAU to get it certified as an official, actual moon of Neptune.
N14 because it is the 14th moon of Neptune overall.
That's correct. And then we got to propose a name. Now the names of the moons of Neptune, remember Neptune is the Roman god of the seas, so for that reason all of the moons of Neptune are named after Greek and Roman mythology of the sea world. And the name Hippocamp actually refers to that creature that you've seen maybe if you've ever looked at some old storybooks or even Roman mosaics. The god Neptune would ride a horse, but that horse was actually the head of a horse and the tail of a fish, and that was called a hippocamp. That was a name out of mythology, so we realized it was compliant with the rules for naming a moon of Neptune. The rest of the story, however, though, is that I'm a scuba diver, and I am very fond of seahorses. They are the weirdest little creatures, and I've seen them in their natural habitat a number of times. Hippocampus is the scientific name of the seahorse because it resembles that creature that Neptune would ride on, and but for that reason, essentially, I got to name this moon of Neptune after one of my favorite sea creatures. That is a real sea creature, not just a mythological one.
Yes, that's awesome. And was this your first experience getting to name a moon?
I'm just laughing because I think Matt knows the answer to that question, and maybe some of the viewers do too. Back in 1990, working on some Voyager data that was at that time almost 10 years old, I discovered Pan, which is still the innermost known moon of Saturn. And then around 2006, Jack Lissauer and I were using Hubble to study the Uranus system, and we found two moons that are named Mab and Cupid. And then a couple years after that, working on the Pluto system, I was the discoverer of Kerberos and Styx, two little moons of Pluto. And now we're sort of taking a step back closer to the sun, my latest discovery being the being Hippocamp.
Right. Got to add Neptune to your list of planets around which you've discovered something, and there's also some rings too. Right?
So there's a ring of Jupiter I found back in the 80s, again using Voyager data, again sort of using special image processing tricks to see things that were kind of fainter than you might otherwise have thought were going to be detectable in the data, and then two thin, narrow, faint rings of Uranus back working with Jekyll.
Same time as Mab.
Yeah.
Yeah. All right, so let's start diving into the science of Hippocamp.
Yeah.
How big is Hippocamp? Like, should we be guided by how big those pixels look?
No. That's a good question. So Neptune is shown to size. Essentially, every other object in here is much smaller than the size of an individual pixel in the camera. The pixels, trying to remember the number exactly, I think it's of order 900 kilometers. So that's way bigger than even Proteus, which is 400 kilometers across. Hippocamp, the best we could determine, is 34 kilometers across, or about 20 miles. So it's the size of the, we're here in the Bay Area, it's probably roughly the size of the San Francisco Peninsula. Lengthwise, it's the size of Manhattan. It's that kind of a size. This is a very small object, and that's why it's faint. But it's not faint. The reason it's faint is because it's smaller than a pixel, not because it fills a pixel.
Right. Okay, so in order to get an idea of how big it is, you need to make an assumption about how bright it is. Is that correct?
Right. All we can really do when you have a dot like this, we get a sense of its size, but only if you assume how bright the surface material is. Now, all the other inner moons of Neptune are rather dark. They generally reflect about 9% of the lights of the sunlight that hits them. So that's almost as dark as asphalt. So that's very dark. But nevertheless, because they're all the same brightness, surface brightness, we can kind of safely assume, it's a reasonable assumption, that Hippocamp probably also reflects about 9% of its sunlight. And so using that information combined with the total light that comes off of it, we can get the idea of a size. Okay. And that's how we came up with 20 miles.
So if it turns out that Hippocamp is brighter than the moons around it, then that would mean it's correspondingly smaller.
That's correct.
Because what you really measured is how much light is reflecting off of it.
That's right.
All right, that makes sense. So we've been kind of talking a little bit about how Hippocamp has a strange orbit. It has this relationship with Proteus. So why don't we start to get into that?
Sure. Actually, I should first clarify, Hippocamp doesn't have a strange orbit. It's on a perfect circle in orbit around Neptune. What's strange is where it is, not how its motion is. And in fact, we've been able to figure out its motion to so much precision that that's what enabled us to say, not just where was it in 2004 when we have our earliest data, or in 2016 when we have our latest data, but we could push that all the way back to 1989 and say, where was it in the Voyager images? And so that was what enabled us to do a search that ended up being fruitless, that we did not see it in the Voyager data. But it's on a perfectly circular orbit, but that orbit is surprisingly close to Proteus. Proteus is actually not visible here. Let me pull up the one that actually shows Proteus, so we're talking about something we can actually see. Okay, so this is a different image. Now here's Hippocamp and Proteus. Proteus is the largest of these moons. It's about, let's see, I remember it's 400 kilometers across, so that must be 300 miles.
Okay, we should probably orient our listeners to the larger Neptune system before we go on, right? So Triton is by far the largest moon of Neptune. That's a world type of a moon.
Yes, let us
and let's do that, and then we'll get back to Proteus.
Yes. Okay. So here we have the entire system as well. Not even then quite the entire system, but Triton is a great big moon. It's almost the size of Earth's moon, about the size of some of the larger moons of Jupiter and Saturn. It's going around backwards. So we believe, based on everything we know about Triton, is that Triton is a captured object. Triton fell into the Neptune system probably very early in the history of Neptune, a few 100 million years into the history of Neptune, more than 4 billion years ago. And when it showed up, it took whatever satellites and rings there were around Neptune and it just tore them apart. And it spent some time eventually landing into this orbit that is mostly circular, although backwards. It's going around Neptune the wrong way. But once it finally tilted by about 20 degrees.
20 degrees.
20 degrees. So at that point, the rest of the Pluto inner system could reform into the system we see today. So this is kind of Neptune 2.0 to begin with. But what's particularly strange is that Proteus, being a relatively big moon, it raises a tide. It raises a little bit of a bulge on Neptune, and those things interact in a way that causes Proteus to be spiraling outward. The same thing is actually going on with the Earth's moon. The Earth's moon is moving away. The Earth is moving away from the Earth at about an inch per year. In a similar vein, Proteus is spiraling outward from Neptune. So we can play that process backward, and if you go back some maybe 4 billion years, Proteus here was basically somewhere near around that red line, which is where Hippocamp is today. And that makes no sense because Hippocamp is 400 kilometers versus tiny little
Proteus is 400
I'm sorry.
kilometers.
Proteus is 400 kilometers. Hippocamp is somewhere around 15 or 30 kilometers, and that couldn't be. Basically, Proteus should have eaten Hippocamp if Hippocamp was there at the time. So instead of saying
Hippocamp won't migrate, its orbit won't migrate as quickly as Proteus is because it's so much smaller. Because it's the mass of the moon acting on Neptune that causes Neptune then to act back on the moon, which causes the orbit to spiral outward. So the mass of the moon is important.
That's right, that's right. So Hippocamp stays where it is and Proteus comes outward. So when they were together, Hippocamp could not have survived. So our better idea is that Hippocamp is a chip off of Proteus. And in fact, there's some nice circumstantial evidence for that because there's an enormous crater on Proteus. I can show that to you. It was imaged by the Voyager cameras. And let's, if I can find that just a moment. Where is that? Yeah. So here is Proteus. I can just zoom in a little bit. Okay, so Proteus has this big missing gap there. That's actually the hole left by a big crater. That crater is essentially the size of Proteus. So something hit Proteus way, way back in the early history of the solar system. And when it did, it spewed out an amount of material that is about 50 times as much as what we see in Hippocamp today. So the idea is something hit Proteus, you had this big cloud of material that formed into a big ring. Proteus kept on migrating outward, and some of that little bit of that material formed together to be Hippocamp. And that's our best understanding. That's the only story we've come up with that's consistent with everything we know about these two moons and about the history of the Neptune system.
All right. So would you think it's fair to say that Hippocamp is a fossil or a clue that tells us something fundamental about Neptune's history?
It certainly, I think it's a dramatic illustration of the fact that collisions, basically things falling into Neptune, comets for the most part, have played an enormous role in this system and probably in the Uranus and Saturn system as well, where some of the smaller moons actually have been broken apart multiple times, and then they come back together again, and then another comet falls in later and breaks them apart again, and so on. The idea that some big impact broke this piece off of Proteus, it formed where it was, and then not only that, but the fact is that this object is on a perfectly circular orbit. One of the things that probably means is that it's gotten broken apart, become a ring, and once you're a ring, everything kind of circularizes just right, and then it accretes back together into an orbit that's on a perfect circle. So there's a big story here about collisions just pounding away at the Neptune system over the years.
So, thinking about the observations you were making while you discovered Hippocamp, we talked briefly about the rings of Neptune and the arcs.
Yes.
Did you find any interesting? I guess this was long ago. So the arcs and the orbits of the arcs have been an ongoing issue. I don't know if we want to say anything about.
Let me. I will say a little bit, just a little bit, because we've got another story to tell. So that's previews of coming attractions at this point. But here we go. So here are the two arcs that exist now. This is from 2004. But back in the Voyager days, there were 4 arcs. And over the time between 1989 and 2004, the leading 2 arcs, they're all going around together, the leading 2 arcs basically dissipated, but the trailing 2 arcs are almost exactly the same today as they were in 1989. And that's a real puzzle, because if we understand dynamics correctly, if you take an arc and leave it in orbit around Neptune, that stuff should basically spread out and become a ring very, very quickly. So it's always been a puzzle how those arcs are held together. And we have some ideas about that, but that's kind of still work we're doing, and we're going to have to save it for another day.
Okay. And if something is holding the arcs together, then why didn't it hold all of the arcs together?
That's part of the story.
Way to turn around.
That's another part of the story.
I love the Neptune ring arcs, so I just had to mention them briefly.
They're stay tuned, but that'll be our next paper, maybe in Nature. Who knows?
Nice. What about future observations?
Yeah, there's not a lot we can do with Hubble beyond that. So we've got a dot, and if we look at it with Hubble again, we would get dot measurements, and they would probably be pretty much where we think it is now, because we know this orbit very well. So I don't think there's a really strong motivation to actually look for Hippocamp again anytime soon, but that day will come certainly when JWST, the James Webb Telescope, goes up. It will be able to see the Neptune system with a clarity that is orders of magnitude beyond this. And then, of course, the best way to really understand the Neptune system is to send an orbiter there. And that day may come. NASA and the European Space Agency are starting to talk about potential missions to either Uranus or Neptune or both. So maybe someday in the 2030s or so, we'll actually have an orbiter at the Neptune system, and we'll be able to count craters on that little dot instead of just saying, oh, there it is.
Yeah. In addition to James Webb, there's also ground-based projects to build a 30-meter diameter telescope, which is also...
Yeah, that may help us. I'm not convinced that even a 30-meter telescope from Earth could detect this object. It is just that small. And but I'd be happy to prove it wrong. Let's say that for sure.
Nice. All right, we have some questions that have been written in by you, our listeners. Thank you very much for listening. We really appreciate your support. Let's see, is there a new telescope that will replace Hubble, asks Gilbert, and I think we just answered that question before I actually...
Yeah, the JWST is going to be several, how big is it? It's an enormous dish, and it will be in orbit outside the orbit of the Earth. It won't be orbiting around the Earth, it'll be a little bit further from the Sun, but it will have extraordinary capabilities for studying a system like the Neptune system.
Let's see, Stephen asks, what is the density and mass of Hippocamp? We covered that a little bit already, but
yeah,
go ahead, Mark.
The answer is we don't know. The answer is it's a dot. So we can get the idea of, so first of all you have to assume how bright the surface is in order to get a size, and then if we wanted to know the mass we would have to get the density. It's not big enough by itself to show its gravity effect on anything else, so we can't make a direct measurement of its gravity at all. It's just not possible. So it's probably got a density that's kind of like a thousandth, or it's got a mass about the thousandth of that of Proteus, but even Proteus we don't have a good mass for, because even Proteus is very hard to know what its mass is.
Jason asks, is there any land on Neptune?
Is there any land on Neptune? Neptune is a gas giant. That means that everything you see, and of course that's just a fake blue blob that I drew in because Neptune is overexposed here, but anything you see when you look at Neptune is gas. And there is a solid core way down inside, but and there you could, I suppose, call that land, but it's basically going to be under just enormous gas pressure from the most of Neptune is just the gas pressing down on the small core inside. So there really isn't land per se, at least none that I'd want to build a house on.
Yeah. Steve asks, is a retrograde orbit like the orbit of Triton, does that always indicate that the object has been captured?
I think the answer is probably yes. At least we don't know any good stories for how a system can form. The idea is most of the planets, Neptune, Uranus, Saturn, formed out of disks, and everything's rotating around. The stuff in the material becomes the planet itself, and then later on the things that get left behind start to form the little moons. But if that's the case, everything's going around in the same direction, so the fact that Triton is going the wrong way is almost a sure bet that it was a captured object.
Very nice. All right, well, we are moving on now to the part where I read off places that people are listening to us right now from. People all over the world, we're very grateful for your interest and your support. We have a listener from Kurdistan, from Australia, from Ireland, Cincinnati, Ohio, Devon in the United Kingdom, Houston, Texas, Staines, UK, Michigan, Bosnia, Cologne, Germany, Lisbon, Portugal, Lille, France, Darwin, Australia, that's up on the north coast, I believe, Monza, Italy, Spain, Russia, New Zealand, and Louisiana. Thank you for just the worldwide interest and support for the SETI Institute. We couldn't do any of this without you. So I think we're going to wrap up. We do not yet have the details for our next Facebook Live, but it will probably be next week. So keep watching the Facebook feed for details regarding that. We do have a SETI Talks for those of you who are local to the Bay Area on March 13th at the SRA International Auditorium in Menlo Park, California. Mark Showalter, along with Ross Beyer and Alan Stern, will be here talking about the New Horizons, the recent flyby of MU-69 and the science regarding that, and I think what's next for New Horizons. Right. That will be, for those of you who are not local, that will be recorded and posted to YouTube and Facebook. So, thank you very much for listening. Once more from the SETI Institute in Mountain View, California, we are signing off.